Okay, in this lesson we are going to talk about how to compute the slope of a non-vertical line given 2 points. We've already seen how on a graph we can look at the ratio of the change in the y, or how far up we have to go from one point to the next, compare it to how far we went on the horizontal or the x direction, right or left. And if looking at that ratio, we could find the slope, but now we can do it with just knowing the coordinates of points. So that's going to be a little bit different. It's going to involve a formula. So let's look. So let's do a couple examples like we did before. So on example 1 and 2, go ahead and pause the video and find the slope for example 1 and 2. And then you can also look at example 3. Okay, so when I look at this example 1, what I notice is that I can find a place on this graph, and here is one of them. I can go over 1, making that my point P, and then that's my Q, and then I come up here, and I can find, so this is my PQ, or my distance of 1, so this right here is my slope. And so it's that height on the graph right there. So my slope here is going to be 3. So M equals 3 on this graph. I could have taken all of this down to the origin, which, let's see if we can get it right there. Right here. You know, I could have used my transparency and moved it over there and read the slope directly on the y-axis, m equals 3. Okay, let's look at example 2. So in example 2, I can find a spot again where I can move a distance of 1 on the x-axis and see how far up the line is either rising or falling. In this case, it's rising. So, and then this distance here, remember this distance is going to be my slope. And so the slope here is m equals 2. And of course, I knew both of these were going to be positive slopes because as I move from left to right, the line is going up. It's rising. It's a positive slope. Okay. So in example 3, the note up here says, what's different about this line compared to the last 2 examples and all the ones that we did in lesson 1? And you may have noticed that what's different is when I move over from any point here, so I'm going to find a point, let me get my pen, I'm going to find a point like this one right here, and as I move over that distance of 1 on the x-axis, the line rises, and I can see that this distance here is going to be my slope because it's the amount that the line rises for this 1 unit change in x. The problem is, even if I move this down, move this down to the origin where I can read it, I can't tell. Based on the units on this graph, I cannot tell what that number is. It's a fraction, and the grid lines on my graph don't allow me to read that number. I know that it's the slope, so I know that the slope is less than 1, a little bit less than 1, but I don't know exactly what it is. So we need another tool to be able to find out what the slope on a graph like this is. So let's look at that. So let's go back to the diagram that we had where we looked at the definition of the slope, and we said that the slope is this height for a 1 unit move on the x-axis. If I move 1 unit in the positive x direction, the slope is whatever height the graph is at that point. So we call that distance QR the slope. Well, the slope is actually this ratio too, like we saw before. It's the ratio of QR, that height, compared to PQ. It just so happens that we've made PQ equal to 1 in all of these situations. But actually, we can look at this ratio for any length of PQ, and this will also be the slope. So M equals this ratio here. So let's take a quick look at example 2 again. In example 2, we found that the slope was equal to 2. And we found it right here. We found a change of 1 on the x-axis resulted in a change of 2 in the height of the line. So that was a slope of m equals 2 by definition. Here it is, m equals 2. So let's use what we just talked about and find another slope triangle here that has, and I'm going to use a different color, that doesn't have a unit change of 1. So let's go right here and up. All right, and so there's another triangle, and if we look at that ratio of the how far up we go to how far over, we're going to get a height of 4 and a change of 2 here, 4 to 2. A ratio of 4 to 2 is the same thing as a ratio of 2 to 1. And so we can see that we really can use any horizontal change, and those ratios are going to be the same, all right? And so the reason for that, and we talked about that in the last lesson, is that the slope is also the unit rate. So in this case, the unit rate here is 2 to 1, but this rate is equivalent to it, 4 to 2. Okay, so but what I want to show you now is geometrically why that's true. Let's look at these two triangles, and you might notice that they look like similar triangles. To show that they're similar triangles, we have to prove that they have at least 2 angles in common. We have to use the angle criteria. Remember that when we talked about similar triangles? And so let's talk about these triangles. What 2 angles would they have in common? Well, they both have a right angle here because they're on the grid lines, right? We've set them up that way, so they both have a 90-degree angle. And so what we need to show is that they have another angle in common. So obviously these angles right here are coinciding, aren't they? And these angles must be equal. But let's talk about why that's true. Let's talk about this angle right here first. You might notice we've got some parallel lines going on here. So I'm going to use some green to show our parallel lines. I'm going to show a couple parallel lines and then a transversal coming through right here. So now we've got a situation where we can say this angle here and this one here are corresponding angles of parallel lines. And we know from our work in geometry before that those angles are going to be congruent. I could translate this angle right up here on that parallel line and show that those two are congruent. Okay, so corresponding angles of parallel lines, and so we've got those 2 angles congruent. And the same thing is true here. And let's look at the third angle in this triangle, and we see that they're already coinciding. So these two lines are the same. So this angle is shared by both triangles, so it's the same. We're going to look at more examples of this and see that even if they're not drawn on top of each other, that we could show that these angles would have to be the same by the same reasoning of parallel lines cut by a transversal. Okay, so these these two triangles are similar. Well, what does that do for me? Well, when I have similar triangles, I know that the ratios of corresponding sides will be proportionate. And so I can look at the ratio of the long side to the short side here, and notice that 4 to 2 is going to be congruent to 2 to 1. So this isn't going to only hold for this particular line, it's going to hold for any line that we look at. So let's look at another example. Okay, so let's look at example 3 and kind of analyze it again. So we had shown on this one that when we did this 1 unit change, we couldn't read, because it's not an integer, we couldn't read the value of the slope there. So let's look at let's find some other good points on this line. And I see some, I'm gonna look here and here. I can draw a triangle between these 2 points. And if I go over 3, I go up 2. I'm gonna find another one. Let's do it in a different color. If I start at that point, whoops, come over there, I think this will work, and up that distance there. So we've got 2 triangles here. Neither of them have a horizontal change of 1, but we can deal with that, right? This one is 3 and 2. This one is 1, 2, 3, 4, 5, 6, and 4. All right, and let's look again and just prove again that these are similar triangles by looking at the angles. We've got a little bit more room here. So we've got our right angles here. And then we can draw, I'm gonna just superimpose these parallel lines here, like so, and I've got a transversal. And here we can see that this angle and this angle will be equal because of the, let's get that angle and that angle are congruent because they are corresponding angles of parallel lines. They're in the same spot. They're both like below, you could say, the parallel lines and on the same side of the transversal. That makes them corresponding angles, and corresponding angles we know are congruent. All right, so these are similar triangles. So what I know is that the ratio of their sides is always going to be the same. And we can see that here in this example. So we've got 2 ratios, and we've determined that these are going to be the slope because the slope is the unit rate, and these constant rates are going to be equal to that. So what do we have? Well, this one we've got, let me get some different color here. We've got 3 and 2, and over here we've got 6 and 4. So if I look at those ratios, the ratio of 2 to 3 and the ratio of 4 to 6, I notice that that ratio of 4 to 6 can be simplified to the ratio of 2 to 3. So that slope is 2/3. And if we get a closer look at right over here where we drew up, going up and up to the line, you'll notice that we went about 2/3. If we brought that over to the y-axis here, it would be this value right here. So m equals 2/3 in its simplified form. So what that slope is telling us is that for every 3 units over, the line is going to go 2 units up. Okay, so what we've seen in those couple of examples is that we can actually pick any 2 points on a line and calculate the slope from them. And often all I have are coordinates of points. I don't want to draw the graph so that I can count off these spaces. I want to be able to calculate this ratio without having to do that. And so that's what we're going to look at right now. And so if I have this situation here, I have the coordinates of P and R, and those are the 2 points that I want to find the slope between. And I also have the coordinates of Q, which is the, shows me this vertical distance and horizontal distance here. And so before we do that with just these variable coordinates, let's do a numeric example that shows the same thing. So let's look at a sample that has numbers in it. Okay, so if I am here on the coordinate plane and I've got these points, I don't have the grid lines here, but I have approximate distances. But if I want to find this distance, so I know that the slope is this ratio, right? It's the ratio of length of QR compared to the length PQ. Okay, and PQ does not have to be a distance of 1 because I know that it's this general ratio here. So I need to find these two lengths. Here's QR and here's PQ. And so to find, pause the video and think about what those distances are and how I could calculate them. Okay, so you might say, hey, I don't have grid lines, but I can see that this distance QR over here, the y coordinate's going from 2 up to 4, so that's just 2 units right there. So QR, and let's write it over here. So QR, the length of QR, is, I can calculate that by saying it's 4 minus 2. Whoops, 4 minus 2. By just looking at these y coordinates here. Okay, and in the same way, you might have noticed that for PQ, I can say, well, in PQ, I can, even though there's no grid lines, I can see that the x-coordinate goes from 1 right here up to 6 over here. So from 1 to 6 is PQ. So this distance here is going to be the difference between those coordinates, 6 minus 1. So I can see that PQ right here is 5 and QR is 2. And so the slope of this line would be QR, which is 2, over PQ, which is not 7, it's 5. 2 over 5. The ratio of 2 to 5, or 2/5. The slope of that line would be 2/5. All right, so what I want to do, though, is I don't want to have to find this point Q. I don't want to have to use that point. I want to be able to just use P and R, because that's what I'm going to have, is the points on the line. And so notice, though, that I can find those points. Those coordinates are found in P and R. So let's look at that. Notice that in the points Q and R, which coordinate is the same? Okay, well, I go from Q here up to R. They have the same x coordinate. So the 6 is found in both of those points, Q and R. And then look at the points P and Q. The points P and Q right here they have the same y coordinate. Look, here's the y coordinate right here. So when I go from P to Q, the y coordinate does not change. There's my 2. And so I could just look at the points P and R and I could say, oh, look, the difference in the y coordinate is 4 minus 2 it went from 4 to 2. And the difference in the x-coordinate is 1 going up to 6. Okay, so that distance there is recorded right in the coordinates of P and R. So take a moment and think about that. I can kind of think of it as, you know, cutting out the middleman here. I don't need the information in point Q with the 6 and 2 because that information is in my coordinates of P and R. It's right here. Okay, so let's go back to a general case. So here, instead of numbers, I've got R1 and R2 are the X and Y coordinates of point R, and P1 and P2 are the X and Y coordinates of point P. And I have this on the coordinate grid, and I am going to try to create a formula here. Not try, we're going to do it. We're going to create a formula that we can use to find the slope between any 2 points. And remember, we've said we don't want to have to find point Q. We just want to deal with points on the line. And we said that all the information in point Q can be found in points P and R anyway. Okay? So what I want to do is I want to have, remember our slope is this ratio. It's the ratio of the vertical distance to the horizontal distance, length PQ. Okay, so it's that ratio. So what I need to find these lengths here. I need to find this length QR, and I need to find the horizontal distance PQ right there. And so we're going to do that just using the coordinates of points P and R. So our slope is going to equal, now if I look at this vertical distance QR, this is the red right here, what I notice is that it is, the Y value is going from this up to here, and I could even draw a little dotted line over to the y-axis to show that. So what it is this distance here is, again, the difference in the y coordinates of the 2 points. So it's the difference between R2 and P2. So I can write it that way. The difference between R2 and P2 uses subtraction, right? So I'm just going to subtract the y coordinates, R2 minus P2. In the same way, to find that distance along that's horizontal distance here, it's the difference between these x coordinates. And let's draw some lines for that. So I've got, I can go right here, you know, and drop a line down. And it's this distance along the x-axis here. It's the same distance here. So it's the difference between, you know, going from P1 up to R1, because that is the coordinate down here on the x-axis. So it's the difference between the x coordinates. So I can write that as, and the larger one here would be for this point R. So I can write that as R1, the x coordinate of point R, R1 minus the x coordinate for my point P minus P1. Okay, and so that's how I'm going to calculate the slope. And notice I did not need to use the coordinates of our Q point here. We could have, but we didn't need to because all of that information was in P and R. So I've got the difference in the x coordinates, the difference in the y coordinates in the numerator of this fraction, or the first part of the ratio, compared to the difference in the x coordinates. Okay, so some version of this formula will be our formula. Now, you're going to see it written slightly differently in the lesson summary, and you'll see it written differently other places too. Just depends on how you label your points. Will be how you write this ratio. But let's look at what the meaning of it is, because it's easy to forget a formula, but if you understand what's actually going on, it's much easier. So another way we could talk about slope is to say that slope is equal to the change in y compared as a ratio to the change in x and in the x values, okay? So notice that y is in the numerator and x is in the denominator. That's because our ratio, we're wanting to compare, slope is going to be larger for larger changes in the y, for greater height in the change of that line compared to certain changes in x. So if x changes 1, if there's a big change in y, that's going to be a big slope. So if we put y in the denominator, that would be opposite, right? Those would be smaller values for m. So think about that. We're looking at how much does that graph rise. And so the change in y ends up in the numerator of that ratio, or in the first part of that ratio. So it's the change in y compared to the change in x. Well, where do we see that over here? Well, QR was the change in y, and PQ was the change in x. And over here, this is the change in the y values. This is the change in the x values. Slope is also referred to as this, and this is how I always would remember it, to know which one to put in the numerator denominator. As I think of slope is rise over run. So how far does the graph go up compared to a distance over? So the rise is the up or down, the run is the left or right. Okay, so change in y, change in x, rise over run. Here's the difference in the x, or difference in the y compared to the difference in the x, and this is kind of more geometrically stated. So all of those are ways to think of the slope of a line and being able to calculate that ratio. Okay, so let's take a look at what happens. How does our formula work on horizontal lines? Well, it works just the same. So here's a horizontal line, and here's two points on that line. And so if we look at the slope being, kind of the difference in the x over the difference in the y, well, so between this length PR, the length of PR is going to be the distance between those 2 points on the x-axis. But what's the difference in their y coordinates? Well, notice for any 2 points on a horizontal line, you look over here, oh, their y coordinates are the same. And so when I subtract them, I'm going to get a big 0. So the change in y is nothing on a horizontal line. There is no change in y. Doesn't matter what the change in x is, there's no change in y. So the slope of a horizontal line using our formula is 0, which is what we wanted it to be. We wanted it to be 0 because it's not positive, it's not negative. The only thing it could be is 0. Okay, let's take a quick look at the lesson summary, and then I want to work through the exit ticket with you because we haven't done a lot of examples here, and then you can be on your own here. Okay, so the slope of the line can be calculated with any 2 points. We saw that those slope triangles are similar, and therefore any slope triangle we draw is going to be similar, and so that ratio of rise over run is always going to be the same. And down below, we have for points P and R with coordinates P1, P2, R1, R2, where the x coordinates here, P1 and R1, are not equal, the slope of the line can be calculated with this formula. And I promised you this would look a little bit different. What's different here is that the P and the R in both numerator and denominator are reversed. All right, so you'll see that you'll see later that it doesn't actually matter which order these points go in, that the slope of m, the slope m will be the same regardless. You'll get the same value even if you reverse the order of the coordinates the way that you calculate it. All right, and there's a reason for that, and maybe you can figure that out. And there's a statement here, the slope of a vertical line is not defined. Remember, for a horizontal line, we found that this ratio just ends up being 0 because the y-coordinates are the same. But if it's a vertical line, what happens is the x-coordinates are the same, and then you get this situation where you're dividing by 0, and we can't do that. That's undefined, and so the slope of a vertical line is not defined. Okay, so let's look. Why don't you pause now and give the exit ticket a try, and then come back and I'll work through it together with you, and then you should be ready to go. Okay, so here's one thing you could have done. There's many ways you could have done this exercise, but I picked the points 3, 2, and 9, 5. And I calculated the slope. So notice I took the difference in the y coordinates, which is 5 minus 2. That gives me this, this distance of 3 right here. And the difference in the x coordinates, which is 9 minus 3 down here, which gives me this distance of 6. And I noticed that the slope is 5 minus 2, which is 3, divided by 9 minus 3, which is 6, which is 3/6, which could be simplified to 1 over 2, or 1/2. I want to show you how I could have picked another set of points, even some negative values. So I could come down here and let me do that quickly. Okay, so these 2 points here, 1, 1, and -5, -2 are also on the line. So I should be able to use those in a slope calculation. So the difference in y would be 1 minus a -2. And the difference in x would be 1 again, minus a -5. All right, and notice that if I do my subtraction carefully, I'm going to get a difference of 3 and a difference of 6. And I can see that here on the graph. I'm going to draw over my, right there. That's the same slope triangle, just with negative coordinates. And so I get the same slope of 3 over 6, which is 1/2. It doesn't matter what I do. And I'm going to show you one more thing, and that's if I reverse the order of the coordinates, what I would get. So let's go down here to these numbers. What if I did m is equal to 2 minus 5 over 3 minus 9? Well, in that case, I'm going to get -3 over -6, which is still positive 1/2, because negative divided by negative is a positive. So it doesn't even matter which order I do these points in, as long as I'm consistent. I always have to use, if I use 1 point first in the numerator, I have to do the same thing in the denominator. Okay, but we know that this line had to have a positive slope, so if my calculation gave me a negative number, I know I need to go back to the drawing board and check it again. Okay, so there's the exit ticket corrected, and you should be good to go for the problem set.